So the quiz is done. We're going to discuss the video analysis that you worked on yesterday. Again, it was a little rough kind of getting started. Every time that I teach video analysis, the first time it's a little bit hard. It's just the nature of learning a new technique and a new skill. On Monday, I think we will do another round of video analysis stuff. So the skills that you have learned and are working on mastering, then we will, kind of put those together and feel like we can actually use them. So I went through while you guys were quizzing and did the video analysis again to get some data. So if you got data, then go ahead and use your data and we'll compare. Okay, if you didn't, get out a calculator and a piece of paper right now, because I want to have you go through the process. Again, even if you didn't get this part really done and you didn't get it really figured out, I don't want the concept to be lost on you. Okay, so we're going to take a look at what we did last time. So yesterday, when we started the conversation, I said we're going to try and prove Newton's third law. That was my goal, right? I've been claiming this for a week, and some of you are just okay with that. Some of you don't seem to have strong feelings about whether or not I'm right, but some of you are getting upset about that. So we were claiming that the forces have to be equal. We did some algebra to prove, because I can't measure the forces on the video, that if I can say that the velocity final times the mass equals the velocity final times the mass, that hopefully will convince you that these forces are the same. So I just want to remind you of kind of the big picture of what we were trying to do. So velocity final times mass, that's our goal. I'm going to cut and paste. Oops. Let me get a new one. So this is really what we want to show. So I'm going to just throw that right here, just to remind ourselves that's what we're looking for. So this is just a screenshot of the picture. The reason I wanted to show you this, number one, was to make sure that the dots make sense to you. Okay, again, the dots are coming. In my case, I did it from the front quarter of the cart. So doop, 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 doop. And this also has the masses. So right now, before we go any further, I just want to make sure that you see those masses and that we know what's what. So I need somebody to pick which one's going to be A, which one's going to be B. Once I want to let you pick which one you want to be A, the young ladies or this gentleman over here? The girls. The girls, all right. So the mass of A, let's write this down. So the mass for A is going to be the mass of Christine plus the mass of Haley plus the mass of the cart. Okay? All of that added together. So you've got calculators out. If you don't already, go grab one, because I need you to do this math for me. All right, so we've got, it looks like 57.8 kilograms plus 68.6 kilograms plus 22 kilograms. So I need y'all to figure out real quick for me what the mass of A, the part A, which is the girls and their cart, what that adds up to. Get a value. So I would like you to do this. You're typing in the numbers. Maya, did you get a number? What did you get? 148.4 kilograms. Then the mass for B, we'll use green, is going to be the mass of, looks like his name is Connor, 69.4 kilograms plus the cart, which was 22 kilograms. So the total mass for B is, maybe you can do that in your head. Maybe you're not so keen on that. Either way, Matt, what'd you get? Oh, he's like, I haven't done it yet. Ryan, did you get it already?
91.4.
91.4. I didn't mean to put you on the spot. It looked like you were done, but I must have misread your face there. All right, so those are my masses. Now I need to find the velocity, right? So the friendly reminder here is that the dots are going to lead us to a graph that looks something like this. So hopefully you got a graph that looks something like this, okay? A nice line for one and a nice line for the other. Can anybody tell me which one's which? Which one is the girls in the cart? Which one is the boy in the cart?
I think I got a negative one for the girls and I got a positive one for the boy.
Okay. What evidence would you have besides the fact that you did it? What if you hadn't done it? Could you tell me based on the picture or based on what you saw?
No clue.
No clue?
The girls' cart has more mass.
Girls' cart has more mass. Okay. So, but this is all about velocities.
So it would be they did be supposed.
I feel like, Jordan, I feel like you were there, but then you just kind of stopped talking.
Wasn't it smaller velocity for the girls' cart than the guy on the cart? Yeah.
Does that make sense? Ben, what were you going to say?
No.
You sure?
I was gonna say like the girls are going in the left direction.
Okay, so you could totally do that, right? Directional, right? One's positive, one's negative. So that absolutely works. Yeah. Let's do the other one too, though. Let's do all of the physics we can, right? Like, let's get it as certain as we can. Yeah.
So when Jordan said that, why wouldn't it just be like a smaller positive number then? Why does it have to be a negative number?
Why does it have to be negative?
It's moving in that direction.
Other direction.
Obviously.
Yeah, they're moving in opposite directions. So if we're going to call one positive, we got to call the other one negative.
Okay.
Does that make sense? The forces, we had said before that the forces were equal in magnitude, right? But the directions are
So they do that for you?
opposite. Yeah,
Okay.
it's smart. This computer's smart, right? So it says, oh, this one's going this way. Oh, this one's going that way. Yeah, for sure. The other piece of it, Jordan, that I think that you were getting at, I just want to make sure that I'm on the same page as you. Acceleration is F net over M. And if we take that idea and we know that we have a bigger mass is going to mean what kind of acceleration? Smaller acceleration. Smaller acceleration means smaller final velocity, right? Okay. So the smaller velocity, the smaller magnitude of velocity, this one here, is going to be for the girls. Okay. So let's assign those as well. So we've got, I may have misassigned my colors here. The velocity final, that's going to be the smaller value, which is, it looks like this one down here. So my colors are messed up. I apologize. Is that 9.328? So we're going to write that down. 9.328 meters per second. The final velocity for, what was his name, Connor, is 14.94 meters per second. And again, if you did this, you may have gotten a little bit of different values. In fact, I did it yesterday. It didn't save, so I did it again today to get actual values. And my velocity values were a little bit different, right? Because it depends on where you put those dots and how, but it gets close. To streamline this process, I'm going to have 1, 2, 3, 4, 5, 6. I want you, this group right over here, to do velocity final of A times the mass of A. Then I'm going to throw you over with these. You don't have to get up, but just like you're going to calculate and you guys are going to calculate the B stuff. Okay? Go ahead and calculate those and we'll compare our products in just a minute. So mass times velocity. Mass times velocity. Did you get about the same velocities as I did?
I got 8.611.
Those are pretty cool. Yeah.
I got 11
for this one.
Yeah.
Yeah. Well, I mean, they're both a little bit smaller, so that's okay. So we're finding our products. We're finding our products, or a product, I suppose, just one. And again, remember, I'm putting myself out on the line here, right? I claimed that these forces should be the same. We reasoned together yesterday that if the forces are the same, then these products should be the same. So I'm keeping my fingers crossed. that this mass times this velocity is going to be equal to this mass times this velocity. Is it going to be exact, my friends? No, because we're doing science, right? We're humans, we make errors, and science is not exactly perfect if we don't have perfect measurement. But we're going to keep our fingers crossed and keep it close here. So my friends that did A, that did the calculations for the young ladies and their cart, what did you guys get for a product? 1,384 point what? 28. What are the units of that product? Not quite a Newton. It's close though. It doesn't have very fancy units. Let's just write them down. It's going to be a kilogram times a meters per second times a meter per second. It's a kilogram meter per second. Yeah, right? It's not quite a Newton. A Newton is a kilogram meter per second squared. So you could write this as a Newton second if you wanted to be fancy. I don't care. I'm going to write as kilogram meter per second, but it doesn't matter to me. All right. My friends that calculated the information for object B, Connor and his cart, what did you all get for your product? Okay, I got almost that. 1,300, what did you say? 65.51. Again, the units are going to be kilogram meters per second. How do those two things look? Are they pretty close? They are pretty close. Again, not exact. I did the math while you guys were taking your quiz to find out how close they were. And we do it on percentage. Do you guys do percentage difference in chem? Do you guys like calculate percent difference for error or no? I don't know if you do or not. Yeah. So to do percent difference, I'm not going to teach you how to do it, but you subtract and then you divide, blah, blah, blah. This is like 0.1% different when you actually like do the, or maybe it's 1%. It's like very, very close. Very, very close between those two numbers. So, moral of the story, I didn't lie to you, okay? That's the first thing that I just want to make sure makes sense to you. So, we have said now, oh my gosh, that velocity, where is that? There we go. That velocity times mass is equal to that velocity times mass, and then just bringing it back so that we're really on the same page. If those velocities are the same, remember we reasoned through and we did physics to show really that those two forces are indeed exactly the same. Okay? So yay for us! That's super exciting. The other thing that we have discovered here, without even really saying it, is a new quantity. And so I want you to write this quantity down because it's a really important one in all of this material. The quantity is called momentum. The P is silent, okay? The quantity is momentum. And honestly, the quantity of momentum doesn't really have any like physical meaning. It's just an interesting product that tells us that Newton's third law works. The quantity of momentum is calculated. Momentum is P, and it is equal to the mass of an object times its velocity. That's all it is. So if you know the mass of an object and you know its velocity, can you calculate its momentum? Sweet. That's the first question on the homework. Next question. If you have the momentum and you have the mass, can you find the velocity? That's the second question on the homework. Boom, you're done with those. Is that okay? Awesome. So the next thing that we need to do is use our brains and be a little clever. And I want to show you this because this is pretty neat. So I'm going to go back here if I can. We said that this had to be true if the forces were the same, right? But I'm going to add in a little bit more information to this. Because the thing that we assumed from this, I'm going to go way back here, we assumed that these velocities, initial velocities, were zero. Okay. The funny part of this, you guys, is that the initial velocities don't have to be zero for this to be true. You can have two things moving before they interact, and they can move after they interact, and they still have a force between them, and by golly, that force is still the same between them. Are you with me there? Okay. So I'm going to take this thing right here and I'm going to rewrite it, and I'm going to show you how beautifully this works. So if we go like this, we're going to take our momentum concept. I'm going to say that the final velocity minus the initial velocity for an object times its mass, we'll call this one A, equals the final velocity minus the initial velocity for another mass, we'll call it B. Now you may notice that here I've got mass times velocity. Here I've got mass times the change in velocity. Are you with me there? Okay. So this is really saying like the mass times the final velocity minus the mass times the initial velocity. Okay. The change in momentum for object A must be equal to the mass times the final velocity for B minus the mass times the initial velocity for B, the change in momentum for A. Oh, for B, excuse me. Got too excited there. That big, long, scary thing is so important that there's a law about it. It's called the law of conservation of momentum.
Like we did something like that in chemistry, or it was called the law of conservation of mass.
Yes. So science is all about conservation laws. Conservation of mass is true in chemistry. It's not actually true in physics. Wah, wah. Doesn't actually work. The chemists ignore the whole, like mass changing to energy thing. Shh, don't tell them because they get mad. But you're right, they do. Unless you have things decaying, you have mass conservation. In physics, we talk a lot about law of conservation of momentum. All of it really comes back to the law of conservation of energy, which we'll do in the next unit. Yeah. The conservation laws are what all of science is about. It's true. I want to try out a problem with you real quick. This one's going to help you with the rest of your homework questions this weekend that you're going to work on. You've got 2 down, 2 to go. So here we go. Our friend Gonzo, okay, is going to jump off of the front of a canoe. He's got a life jacket, so he's going to be fine. Okay? The canoe is initially at rest. So I'm going to go ahead and draw my little picture here. You can draw a picture too. So here's my canoe, or not my canoe, but Gonzo's canoe in the water. And here's Gonzo. And he's got a little life jacket on, and then he's standing there. There he is. Whee! And there he's going to jump in just a minute. Rah! Yay! All right, so here he goes. So far, so good? Question for you. What is the momentum of Gonzo before he jumps? Why? He's standing still. His initial momentum is 0. Is that okay? Tell me about the momentum of the canoe before he jumps. 0. Is that okay? So the canoe has a momentum of 0 because it's not moving. Gonzo has a momentum of 0 because he's not moving. Nothing's moving, nothing's happening. Now, before we do the math here goes Gonzo. He's standing here, he's ready to go. If he jumps like this, where's the canoe gonna go? the other way. Are you with me there? Why does that happen? Because we had a total momentum of 0 at the beginning. If he gets momentum this way, the canoe's got to get momentum that way. You with me there? They've got to add up to how much? How much do we have to start with? 0. They've got to add up to 0. Momentum has to be conserved. Let's write down what we know. We know that the mass of Gonzo is 55 kilograms. We know that the initial velocity of Gonzo is 0. We know that the mass of the boat is 250 kilograms. And the initial velocity of the boat is 0. What's Gonzo's final velocity? .5 meters per second. He's going to go this direction. The boat is going to go that direction. That's what we want to know. We want to know the final velocity of the boat. Do you think you can find it? Let's give it a shot. I'm going to pull my equation. Let's see if I can do this from one page to another. We'll see how fancy it is today. Copy. Hey, sweet. All right. Does anything go away? Let's change these to G's. What do you mean the second part?
Gonzo equation in the book.
Because the velocities are 0, aren't they? So let's get rid of them. That makes this equation look so much less scary. So now we know that the mass of Gonzo times the final velocity of Gonzo equals the mass of the boat times the final velocity of the boat. That's exactly the same thing we did with the kids on the little carts. Do you remember? It's the same thing. So if you plug in 55 and 7.5 over here, 250 here, you can find that final velocity. Go ahead and do that. Let's see what we get. That is super exciting. Holy cow. How are we doing? Did you get an answer, Maya? What'd you get? 1.65? Awesome. If Gonzo jumps to the right, which way is the boat going to go? To the left. Yeah, we're going to write down that as well. Yeah. All right. We did it, you guys. We made it all the way through. We got a minute before the bell's going to ring, but I'm not going to start something else because we only have a minute. Make sure that you've written down this homework. Make sure that you give these 4 problems a try before I see you again on Monday, okay? So we're going to jump in there. We're going to do a lab on Monday as well. So make sure you bring a charged Chromebook. Please and thank you.